Hey y'all, welcome to lesson 67 of my DP chemistry curriculum. Today we're going over reactivity 1.1.4. The standard enthalpy change for a chemical reaction, delta H, refers to the heat transferred at constant pressure under standard conditions and states. It can be determined from the change in temperature of a pure substance. So we're going to be able to apply the equations Q equals MC delta T and delta H equals negative Q over N in the calculation of enthalpy change of reaction. And we must know that the units of delta H are kilojoules mole inverse or kilojoules per mole. So in this unit, in this section, we're talking about enthalpy and heat transfer, and we're going to be answering the question, how do we quantify energy transfer in chemical reactions? Which the answer is, of course, enthalpy. Enthalpy is referred to as H, that is the unit of enthalpy, and that is the of amount of heat in a system, which is objectively incredibly difficult to measure. So what we do measure, as we mentioned before, is we often measure delta H. That is going to be the change in enthalpy. So we'll measure how a system changes by going up or down, and we usually do that by measuring temperature. Now, it can go two ways. We can have a positive delta H, meaning the system increases in energy, and we refer to that as an endothermic system. We talked about that a little bit in the last video. We can have a negative delta H, and that would be energy being released, and therefore that is an exothermic system. So those are two things to know right away. We're talking about reactions, so I'll say exothermic and endothermic chemical reaction. Now, one other unit that you're going to be seeing a lot of is delta H with this like theta right at the top. And what that refers to is specifically the standard change in enthalpy. Now, what makes it standard is a couple things. One, it's under standard pressure and temperature, as we mentioned up here, constant pressure under standard conditions and states. But the other thing that makes it standard is we're usually referring to 1 mole of substance. So the change is 1 mole. This is going to have units specifically of kilojoules mole inverse. So we're always referring to 1 mole. Now, this one up here will also have units of kilojoules per mole. But if we're actively working with 1 mole of substance that we're combusting, then we would be dealing with the standard change in enthalpy. So one final thing is we've dealt with chemical reactions, but we are now going to be dealing with thermochemical reactions. And we know it's a thermochemical reaction if heat or enthalpy values are given, are provided. So if you're ever looking at the enthalpy, you're dealing with a thermochemical reaction. So just some vocabulary for you. So a good example of a thermochemical reaction might be the chemical decomposition or thermal decomposition of calcium carbonate. Calcium carbonate decomposes into calcium oxide, solid, and carbon dioxide. Now, from the last video, we know this decomposition, and therefore this will have a positive delta H because it is endothermic, 180 kilojoules mole inverse. What this means is for every 1 mole of calcium carbonate that decomposes, we will produce 180 kilojoules. And we know that because it's a standard value. If we were to look at an energy profile for this, or if you're asked to draw an energy profile diagram, it's quite simple. We have our potential energy, and we have our reaction coordinate. Now, on a DP exam, don't abbreviate reaction. I just do it because I'm trying to be quicker. CO3, and then up here we have CaO plus CO2, and this is our delta H, which we know equals 180. So that's our energy change. Now, this is something that you will be able to do and should be able to demonstrate on your exams. So how do we actually measure these values instead of just writing them out? Well, this is when we talk back about thermal energy. This is how we're going to quantify these changes. So we'll use change in T to relate to change in H. So change in energy. And we're going to do that through the use of Q. Q is going to be our heat energy gained or lost. So we're going to be using a lot of different letters here, but we're going to use the equation Q equals mc delta T. So once again, Q is the heat energy gained or lost. This will be measured in joules. M is our mass of substance, whatever we're measuring, and that's going to be in grams. C is going to be what's known as the specific heat capacity of a substance. And delta T is our change in temperature. This will usually be measured in Kelvin, while specific heat capacity is measured in joules, grams inverse, Kelvin inverse. So to figure out what all of this means, let's first start off with what the heck is C, our specific heat capacity. This is a definition you do need to know. It's different for every element in every substance, but this is the energy required to raise 1 gram of substance by 1 Kelvin. Something to note is raising it by 1 Kelvin is equivalent to saying raising it by 1 degree Celsius, because while Kelvin does not equal degrees Celsius, a change in Kelvin does equal a change in degrees Celsius because we're just adding 273. So this is something we mentioned very early in videos, that the change in temperature doesn't really matter. So if we're raising by 1 degree plus 1 Kelvin, that's the same as saying plus 1 degree Celsius. You should be used to that change and be doing it automatically in your head as you read problems. So let's take an example and practice this equation and kind of figuring out what it means by doing it. So I'll take a moment to write this and we'll come back in a second. So the equation is, or the problem is, a 150-gram block of copper is raised from 18 degrees Celsius to 75 degrees Celsius. The C for copper is 3.89 times 10 to the minus first, joules, grams, Kelvin inverse. What is the change in heat energy? So we'll be using our equation, Q equals mc delta T. And we're going to start plugging in our values. Our mass of our copper is 150.0 grams. I'm going to keep the units at this point, but once you start using these a lot, you can lose them. Just make sure your final answer has units. Our C we know is 3.89 times 10 to the minus first, joules, grams inverse, Kelvin inverse. And our temperature change is 75 degrees Celsius, or I'm going to lose those units, 75 minus 18, and I'm going to just put Kelvin as my side unit because we're finding the change in temperature. This change in temperature, it's very important. You always do T final minus T initial. It'll help you get the sign correct for Q, whether Q is positive or negative. And once again, when we look at this change, it doesn't matter that the change, we're looking for a difference in Celsius. A difference of degrees here is exactly the same as a difference in Kelvin. So what I do is I plug this all into my calculator, but before I do that, I'm going to make sure my units work. Grams inverse cancels with grams. Kelvin inverse cancels with Kelvin. I'm left with joules. That is what my Q should be in. So as I get to my answer, I get 3,300 3.3 joules. Now, problems will usually ask for kilojoules, so you should be pretty confident in just turning this into 3.30 kilojoules. And we'll explain why kilojoules are important as we move forward, but for now, know that both of these are valid answers depending on what the question is asking. All right, so that's how we use that equation, but when do we use it? What do we do first? Well, to figure out how to use that equation and when we should, we have to look into calorimetry. Calorimetry is what we use to measure changes in heat produced by a chemical reaction. The tool we use in calorimetry is called a calorimeter. So it's a pretty self-explanatory tool. But what calorimeters specifically do is they actually measure temperature changes of chemical reactions. So we can see how temperature changes are useful. Once we have a change in temperature, we can find the change in energy. So we use our temperature change to find our heat change, and that is what calorimetry is used for. The DP does require you to know different types of calorimeters. There are 3 types of calorimeters that we use. So you should be familiar with all of these. The first one is a bomb calorimeter. You should be kind of familiar what they look like. A bomb calorimeter is usually an expensive looking container with lots of layers of insulation. So it's like double walled. You have a thermometer in the top, and then you have a separate chamber for a reaction to happen. Chamber. And surrounding that, you have water that you measure the heat change of through your calorimeter. Now, bomb calorimeters have a very big upside. These are very accurate, and they're used for food and fuel combustion. So figuring out the energy of a combustion reaction from food or fuel. So this is how they can get some energy values for the food that you eat, like the calories on the back of your food products. But there's a very hefty negative for a school. These are very expensive. So you're not really going to see a bomb calorimeter in your studies unless you go into food science. Now, the next two are 2 very common types you'll use. One of them is called a metal calorimeter. Metal calorimeter you'll set up for combustion reactions. What it generally looks like is a ring stand with a beaker and a thermometer, and you have your fuel or combustion underneath. And inside this beaker, you have water. So you just measure the change in temperature of the water as combustion occurs. It has a couple positives. For first off, this thing is really easy to use. It's cheap. We use it for combustion reactions. But you can see the downside. There's a lot of heat loss. So we can only measure the heat that goes into the water, but we also have heat loss out in the surroundings. You have heat loss on the beaker, you have heat loss on the metal rod, you have heat loss everywhere. The next and final calorimeter you'll use is called a coffee cup calorimeter. And you can call it that because it's usually made from 2 coffee cups, one inside one another. So you have 1 cup. Within that, you have a second cup that creates a nice insulative layer. Within that, you probably have your beaker that your reaction happens in with your thermometer. This has a couple advantages. For one, it's also cheap, and we use it for aqueous reactions. And it's not bad, but the main problem with it is the same as the metal calorimeter. There is heat loss. The hardest thing to do in calorimetry is to avoid that heat loss because that's going to skew your results. So these are three type of calorimeters you'll see across the DP exam or even in your lab. Chances are you'll be seeing these two in your school lab. All right. So that's basically a little bit about our calorimeters, but what do we actually do with them? Well, you'll notice they all have thermometers on them. There's these little rods I put it at the top. Should have made that a little clearer. So they all have thermometers because that's the main point. They measure changes in temperature of the surroundings of a chemical reaction. You'll notice specifically they're measuring the temperature change of the surroundings. But when we're looking for enthalpy, we want the change of energy of the system. So even though they measure the temperature change of the surroundings, then we get the Q for surroundings. So how do we turn that into delta H of a system? What do we do? Well, first off, if energy is going into the surroundings, it's leaving the system. So delta H doesn't exactly equal Q. It equals negative Q because once again, if it's going into the surroundings, it's leaving the system. If it's coming from the surroundings, the temperature is going down, the system energy is increasing. So delta H equals negative Q. Furthermore, Q has units of joules. System has units of kilojoules per mole. Or sorry, delta H has units of kilojoule per mole. So usually Q is divided by mole, and sometimes 1,000, depending on whether or not you are doing kilojoules or joules for your Q. So this is the equation you're going to be using. Sometimes you won't have the 1,000 depending on if your Q is in kilojoules, as we did up here. We don't need to redivide. All right. So let's look at a new problem. Let's do another new example. So once again, I'll pause it and come back once I've written out the problem. All right, so our new problem is the combustion of 4.8 grams of ethanol, CH3CH2OH, raises the temperature of water in a metal calorimeter. So we're looking at this calorimeter cell right here by 46 degrees Celsius. What is the enthalpy of combustion, delta H C, for ethanol? So what we're going to do is start out by doing Q equals MC delta T, because this change in temperature is going to be for water in calorimeter. So we need to know how much energy is going into the water in our calorimeter. So our mass is going to be, I did not provide that, for raise the temperature of 100 grams of water. So our mass is going to be 100 grams. Our C is going to be 4.18 joules, gram inverse, Kelvin inverse. And our change in temperature is going to be 46 Kelvin. Once again, we do not need to do any conversions between Celsius and Kelvin as it's the same value. Once we plug this into our calculator, we'll get 1,920, or sorry, 19,228 joules. I know that I'm going to be converting to enthalpy, so I'm just going to convert that ahead of time to 19.228 kilojoules. Save myself a little time later. This is all for the water. This is the heat gained by water, or the heat energy gained by water, a positive value. Now, for ethanol, we know ethanol is going to be losing heat, but we also know that we're looking for delta H, which has units of kilojoules mole inverse, which means I need mole of ethanol. So what I'm going to do first for my ethanol is actually find the amount of moles. I start with 4.08 grams and I divide by the molar mass. For every 1 mole of ethanol, that's going to be 46.08 grams. I know that because all I'm doing is taking 2 carbons, 6 hydrogens, and 1 oxygen, CH3, CH2OH. So all I'm doing is 12 plus 3 plus 12 plus 2 plus 16 plus 1 plus a couple decimals, about 8 of them, and we get 46.08 grams. My grams cancel, and I end up with a value of 0.0885 mole of ethanol. All right, so now I'm finally ready to figure out delta H. Delta H is equal to negative Q over N. And I don't have to divide by 1,000 because I did that already. And I get a final value of negative 19.228 divided by 0.0885, which gives me negative 217 kilojoules mole inverse. And that is my enthalpy of combustion for ethanol in this reaction. Now, one thing the DP will ask you is this value higher or lower than you expect? And the truth is, this is not going to be the correct value because we have so much heat loss out of our system that our Q is likely way lower than it should be, meaning that the magnitude of this value is lower than it should be. It should be negative 3, 4, 500 maybe, even more or less. So you can get these values actually in your data booklet, but when the DP asks you to do the math, you're going to have to do the math. All right. So that was in a metal calorimeter, but what about delta H in an aqueous solution? So we're still going to use Q equals MC delta T. But for example, what if we have a solution of something like copper sulfate and maybe a piece of zinc? And this ends up reacting to produce zinc sulfate and copper. What's going to happen to our solution? What's going to happen to the change in temperature? And how do we use Q equals MC delta T? Because we know this is mass of water, we generally do it as the mass of the water or mass of the substance. And C, we're also going to be doing it for water, but the problem is this is no longer water. This becomes an aqueous solution containing solvents or solutes. So how do we actually figure out the change in temperature? Well, we have to make 2 assumptions. And you're always allowed to make these assumptions here. So assumption 1 is that the density of water is going to be equal to the density of solution. So, meaning that, well, it might be inverse. The density of the solution is equal to the density of water, I should say. Meaning that your solution will have a density of 1.00 grams per centimeter cubed. Meaning that just because you have something dissolved in it, you can still assume that whatever the volume of solution you have is equal to the mass. Assumption 2, C of solution will also be C of water. So your specific heat capacity will also be 4.18 joules gram Kelvin. That will not change. Once you make these 2 assumptions, your reaction is exactly the same as it would be regardless of whether you did a bomb calorimeter or a metal calorimeter. So let's do another example just to kind of test this out and use this kind of knowledge. So I'll pause it and come right. So using the same reaction we have above in this example, we say excess zinc reacted with 150 centimeters cubed of 1 mole per decimeter cubed copper sulfate. The temperature increased by 43 degrees Celsius. What is the enthalpy change in kilojoules per mole? So the first thing we're going to do is find Q equals mc delta T. Now, the mass is of our solution right here, which we're going to assume is the same density as water. So we're going to have 150.0 grams. Furthermore, our specific heat capacity will still be that of water, 4.18 joules gram inverse Kelvin inverse. Lastly, our change in temperature will be 43 Kelvin. So we can get our Q quite easily. It becomes 26,961 joules, which I will convert to 26.961 kilojoules. All right, so there's our Q. But now for delta H, we know that we need our moles. So when we're doing this reaction, we need to know what we're getting our moles of. Now, we know our zinc is excess, therefore our copper sulfate must be limiting, so we're going to be using moles of copper sulfate. Now, this is in solution, so we have to use our equation. Moles is equal to the concentration times the volume. Therefore, and remember that one's right in your data booklet, our concentration is 1.00, and that will be mole decimeter cube inverse. Our volume, well, that's 150 centimeters cubed. We need decimeters cubed. We know we can make the conversion by dividing by 1,000. So this is going to be 0.150 decimeters cubed. Or sorry, that is not inverse, decimeters cubed. That will cancel with that, and we get our mole to be equal to 0.150. So we can plug these values in, negative 26,961 divided by 0.150, and we can get that our final answer is the enthalpy change is going to be equal to negative 179 kilojoule, or 179.74 kilojoules mole inverse. So this is how we use the assumptions. We just don't change our value for mass or C. We use the same values as water, even though this is a solution containing water and not pure water alone. The last thing we're going to cover today in this incredibly long value is how do we account for heat loss? Because we already saw that we're going to have the most common calorimeter have a lot of heat loss, both in our metal and coffee cup calorimeter. So we need to learn how to account for it in our lab setups. The simple thing is we can look at it as we graph our change in temperature over time. So often, if you're graphing temperature over time, make a quick graph here. This would be temp. Degrees Celsius is probably what you're going to be graphing in the lab. You're going to get a graph that looks a little like this. It's going to reach a maximum temperature and then a very, very slow drop off. So this is generally what your graphs will look like. There's a couple key things in this graph, and it's a couple key elements that you need to be able to recognize. First off, right about here is where your reaction is going to start. You notice this is where your reaction starts because that's where the temperature starts changing. So this is reaction begins. Now, the problem is we don't really know where it ends. Often people say right here at our maximum value, which it's always good to point out. So let's go ahead and identify that. Maximum temperature value. the problem is parts of this reaction are slow, parts of this reaction are fast. We know the temperature can increase if this is an exothermic reaction, but why is it decreasing? Well, it turns out this decrease can be explained by heat loss to the environment. So this is our linear heat loss to environment. And it's pretty linear. Now, that heat loss is happening constantly. Even when the reaction is increasing in heat, we're still losing some to the environment, especially because we might have a glass cylinder or a beaker or a coffee cup maybe isn't that great. And this turning point is just where the heat added to the system or added to the surroundings starts becoming less than the heat lost to the environment. And so that's why we get this nice gentle curve at the top. So the reason we need to find this linear heat loss is because if our reaction was instantaneous, meaning it all reacted at once, it wouldn't make this curve. It would shoot straight up. So the key point in this graph is a point that's not even marked, and it's this one right here. This is our theoretical max temperature if heat loss didn't exist. If all the energy went straight into it, we can extrapolate where we should be based on the start of the reaction and the heat loss. So you should be able to analyze these graphs as you move forward. I hope this helps you in your labs, and I hope this helps you understand enthalpy, and have a great day.